All right, we begin. All right, this time for real, welcome period 8. You had a pep rally, and so you did not have class, so you are going to be watching this class for the next like 75 minutes or so. All right, hey, what happened? Yeah, you like didn't do it. That's like bad? Oh man, what's up? That wasn't even that much homework.
Just kidding, I figured it out.
You just figured it out? Let's do 2 of them. How about we just do 8 and 9? Is that okay?
Sure.
All right, can I see this? Okay, it's okay. I'm just going to use the problem. So, number 8. You guys can just look on with the people next to you and check, I guess. Maybe that's even more efficient. But I'll just do one of these more on the board. And F1 equals 8. Okay, and the problem was to find F. Oh, F is a cubic with real coefficients.
Oh, you didn't.
Oh, I think so. For this, there is the long way and the short way. The long way is to say, well, this function must look like, by the factor theorem, since 2 is a factor, x minus 2 is a root, and since 4 minus I is a factor, then x minus since 4 minus I is a root, then x minus 4 minus I is a factor, and since complex roots come in conjugate pairs, 4 plus I will be a factor also, so x minus 4 plus I will be a factor. And then I guess there's only just, the only thing left since it's a cubic is that there's just like another thing A, right? Yeah, I guess this way is really not even that long. This is probably how I would just do it. In fact, this is what you have to do, right?
Yes.
Yeah, there's no other way to do it. I take it back. There's no short way, because I have all 3 roots already. All right, so anyway, what do you get? You get x minus 2, and then the way I think it's a good idea to do this is to redistribute, so you get x minus 4 plus I, and then here you get x minus 4 minus I, and that enables me to multiply this out because these are conjugates of each other, and I get x squared, or some of you suggested that I just leave it as x minus 4 squared plus 1. And at that point, all the complex numbers are gone, or the imaginary numbers are gone, I should say. And so I can just plug in 1 and figure out what A is. Is this what you guys did?
Yeah.
All right, so if you plug in 1 at this point, you get A, that's negative 1, and that is like 10, right? 1 minus 4 is negative 9 to 10, right? Yeah. Okay, and the whole thing is supposed to be 8, and I guess therefore the answer is that A is negative 4/5. Agreed? Why is everyone being so quiet? Yeah, good. All right, so this function all along was negative 4/5, x minus 2, and I like to write this as x squared minus 8x plus 17, but it really doesn't matter how you write it. You can just leave it like that. All right, cool? Stay cool. Okay, good. Then the last problem, can I have this for a second? Here, this is the part that period 8 is not going to understand because I didn't teach them this yet. So 3x cubed minus 33x squared plus 99x minus 54. Okay, so first of all, before you, let's talk about the problem. What is the problem? F of 5 minus root 13 over 2 is 0. And I note that this is a polynomial with rational coefficients. Therefore, if this is a root, then we know that 5 plus 13 over 2 is a root also. And what we want to do is find the other root, the third root. Well, what we can do is to use Vieta's formula, also known as the sum of productive roots formula. That's the fast way to do it. And so if we're looking for that third root, this leading coefficient can only distract us. So we can't do any analysis until we factor that out. So if we factor that out, we get x squared minus 11x squared plus 33x minus whatever that is, 18? What's up? Oh, cube. Thank you. Okay, and so now that I have it written this way, I know, based on the thing we derived last class, that the sum of the roots must be 11 and the product of the roots must be 18. So if the sum of the roots has to be 11, then I can just be like, yo, 5 halves minus root 13 over 2 plus 5 halves plus root 13 over 2 plus this mysterious third root has to be 11. And that tells me that r has to be 6. You can just like basically do the whole thing right. Cool?
Wait, isn't it 18?
Did I do that right? I feel like I did.
Wait, why is it 11?
What's up? Can you let her in? Or the other way to do it is to say that the product of the roots is 54. So we can just be like 5 halves minus root 13 over 2, 5 halves plus root 13 over 2 times the mysterious third root has to be not 54, 18. But this looks hard, but it's actually not that hard, right? Because these are conjugates of each other. So it's just difference of squares. So it's just 25 fourths minus 13 fourths, which is just 12 fourths, which is just 3. So we get 3r equals 18, and again, r equals 6. So that's all you have to do for that problem is just find the third root. All right, how are we feeling about this? Good? Good. All right. Good. All right, so, yeah. Can I erase this?
Yeah.
Going once, going twice? Okay. Yeah. All right, I would like to introduce you to like the big claim of this whole unit on polynomials. It is called the fundamental theorem of algebra. And that's a pretty grandiose name. There are a whole bunch of fundamental theorems. There's like the fundamental theorem of arithmetic, the fundamental theorem of calculus, the fundamental theorem of counting. This is the fundamental theorem of algebra. So what does the fundamental theorem of algebra say? Basically what it says is, we will amend this slightly, but basically what it says is, hey, I noticed that quadratics have 2 roots, cubics have 3 roots, quartics have 4 roots, etc. That always happens. So fundamental theorem of algebra is that an nth degree polynomial has n roots. That's it. But there are some like things worth commenting on, and I would like you to like make some comments now, actually, because some issues. You should be sort of skeptical. You should be skeptical always, all the time, all day long. But especially now, I'm telling you to be skeptical. Shout out all things at once.
Double roots, yeah, or triple roots.
What if it's
0
like half?
squared.
What if it's half?
Yeah.
You can have
That's
yeah,
If 0.
So yeah.
What if it like just doesn't hit 0 like ever?
But
Give me an
then
example.
Like, if you have a graph that's like x squared plus 6, then it just doesn't ever hit 0.
Yeah, so it's like, dude, I know some polynomials just off the top of my head, like x squared plus 6. That is a second degree polynomial, and it has no roots. Counterpoint.
the roots are imaginary.
Not imaginary.
Yes.
X squared equals 0? Wait, no, that's not
Just x squared.
Wait, we're talking about
Are you
functions.
saying, oh, never mind.
Okay, wait, let's deal with one thing at a time. So Young was like, yo, it's not always true that second degree polynomials have roots. But, counterpoint, this does have roots as long as you're treating complex numbers just like any other numbers. Okay, so the real thing we should clarify is that an nth degree polynomial has n complex roots. In other words, if we fully let complex numbers into our heart and treat them just like any other roots, now we can say for sure that an nth degree polynomial has n complex roots, or at least that's clear for quadratics. It's less clear maybe for higher power polynomials, but that's why this is kind of like a new thing. All right, there were some other objections. What was the other objection? Yeah, all at once.
Well, I actually have a different question.
What's your
like
opinion?
1/2 power.
That's not a polynomial. Glad you brought that up. Yeah, what is a polynomial? Yeah, that's just not a polynomial. Like root x is just not a polynomial. Okay, good. I dealt with that pretty smoothly.
I was gonna
Yeah.
say, like, what about, like, is y equals 0 a polynomial?
Well, that's another problem. Yeah.
Like x squared, that's double roots.
Yeah, what about f of x equals like x squared? That appears to have only one root. And I think even last year in Giles you would call that like a double root, right?
Yeah.
And yeah, so exactly, this we call a double root. So all right, like note, in order to, I guess I want this here. Note, in order for this to be true, double roots have to count twice. So double roots count twice, and triple roots, like, etc.
Can we just say n roots count?
Sure, yep. Okay, so let's look at some examples. Let's look at the most chill polynomials possible. Here's a pretty chill polynomial. Consider x minus 2, x minus 4, x plus 6. All right, talk to me about this polynomial.
It's a third degree polynomial. It has 3 roots.
Blah, 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 blah. Good, exactly. Yes, this is a third degree polynomial. It is a cubic. It has precisely 3 roots, and everything's great. Okay, also, a little bit of common sense will suggest how to graph this polynomial. So what do we know about this polynomial? Well, we know where the roots are. So everyone make a picture. Try to do it before I do. I know there's a root at -6. I know there's a root at 2. I know there's a root at 4. What else do I know about this polynomial?
It is third degree.
Right, so you know which direction.
Yeah, the end behavior. Everybody please make the end behavior with your arms for this polynomial.
Wait, which way am I looking?
You have no idea? When x is like a million, this is like a million times a million times a million-ish, right? So it's going to be big. But when x is like -1 million, it's like -1 million-ish, -1 million-ish, -1 million-ish, which is going to be negative huge. Agree? So it's like this. You guys did this with Dallas last year? I hope.
Not
It's like,
the arm thing.
not the arm thing, it's standard math teacher thing. I'll make sure to fire it. Okay, good. So, what do you think this polynomial looks like? Well, actually what you can do is one of those very tedious Precalc A sign charts, and the tedious Precalc A sign chart will reveal, remember this? Will reveal that it's positive if x is bigger than 4, negative if x is between 2 and 4, positive if x is between -6 and 2, and negative thereafter, right? That's the only thing you can do. Alright, so this is basically what this function is going to look like. Everyone cool?
Yeah. We don't know
Alright,
exactly what
note that some people object to my use of the term graph, because this is a pretty weak graph. So I will use for those of you like lawyers in the room or whatever, I will refer to this as a sketch. This is a sketch because basically I'm not actually being accurate at all with respect to the y-axis, follow? Okay. And I also don't know where these relative minima and relative maxima are. For that we need calculus, okay? So this is one thing we don't know, but this is a decent sketch. Everyone happy?
Yeah.
Okay, good, we do more. Consider the following function. F of x equals x minus 2, x minus 7, x minus 7. What's up with this?
Double roots.
Yeah, so superficially it appears to be almost exactly like the polynomial we just saw. Also a cubic, also having 3 roots. Can you see how we would want to treat this like the same as the previous one? Because it's kind of like the same thing, right? And like this is going to have a root at 2. And it's going to have a root at 7 and kind of like another root at 7-ish, almost, right? If you think about it, if you were going to, if this were, instead of these both being 7, if this one were like 6.9 and this one was like 7.1, then you'd be like, you'd have 2 roots that were like really close together. And what would this look like? What's the end behavior for this function?
Same positive.
Also same, right, like this. And so it's also coming like up. Oops, I missed. coming up. And then like I was saying, if it's like 6.9 and 7.1, then it would just go like right, it would cross and then it would like cross again immediately and go back up, right? So now it's like sort of like this. And it kind of gets curvy at the bottom. Yeah, more on that in a second. So this is for reasons like this that we prefer when dealing with polynomials to treat this as like a double root, because like basically it behaves as if it were two separate roots as far as like affecting the shape of the graph and everything like that. Okay, so that's like cool. And then another one is this function now, f of x equals like take x minus 4 cubed. What's up with x? I'm sure you're giving me in a frame.
Yeah.
Okay. What's up with make a graph of this function? Please go.
That's a lot of roots.
Boys are
It looks like X. It looks like X.
Yeah. That way.
Dude, but it's so weird.
No, just like moves to the right?
Yeah, but he's objecting. Yeah, but for all of you guys, I have objections.
Yeah, but it like curves.
Because we caring about the local behavior here. Did Giles make a big deal about this last year? I bet he did, because it's like a math teacher thing. What does the graph of f of x equals x cubed look like if you zoom in on it really, really closely? If you don't believe me, you can plot some points. Like here's the point, if this is the point 1, 1, and that's -1, -1, the graph of x cubed has a very distinctive look to it. And that is, if you think about it, if you cube a number which is between 0 and 1, what happens? Take like 1/2 cubed, what do you get?
Gets smaller.
1/8, right? So yeah, the cube of a number between 0 and 1 is much smaller than that number. And if you cube like, I don't know, if you cube 1/4, what do you get? 1/64, right? So this cube function is pulling small numbers down towards it. And so what you get is this very distinctive cubic-y looking shape in which it gets really flat here. I'm pretty sure Giles talked about this.
He did.
Yeah, this is called the subtle curvature. If he was using my packets, which I think he is, then I even had a whole thing like this where you graphed x cubed versus x squared versus x to the fourth, and you see that each of them gets like smaller and then bigger. Okay, so when you go to graph your x minus 4 cubed, no like kind of just lazy like rah, rah, rah. No, make it look like really actually good. So it's going to come up and it should get flat, really flat in there, and then back up again. Okay, good. This is like the cubic behavior. Okay. Good. I was going to say something else. Oh yeah, and this, of course, we refer to as a triple root. And so this is still satisfying the fundamental theorem of algebra because we sort of think of it as having 3 roots. Okay. All right. Now I want to summarize something that I think you guys did last year. Trish, you can either turn or you can just pick up the camera and put it over there, whichever one you think is easier. All right.
You're
so
lazy.
Consider the following function: f of x equals negative x plus 2, x minus 2 squared, x plus 1 cubed. All right. I want to make a graph of this function, or a sketch. And I want this sketch to be sort of accurate, and I also want to like understand why this thing looks the way it does. So okay, so talk to me. What are some things I know about this function?
The roots.
Yeah, it has a whole bunch of roots. Actually, how many?
6.
Yeah, this is a 6-degree polynomial. Okay, so like, yeah?
-2.
So yeah, some stuff we can just start like doing, right? Like there'll be a root at -2. Of course, when I plug in 2, I also get 0. And when I plug in -1, I get 0 also. Okay, cool.
And you know the points up on the left?
And then, what's up?
No points down.
No points.
Even so it goes down.
Yeah, what is the end behavior? That's something that we can all do right now. What's the end behavior? Everyone do with your arms.
Yeah.
Points up goes down. No, it's 6. Up 1 over. No, it's down. It's a negative.
Let the record show that that many people are cowards and doing nothing, others are all different from each other. It is 6 degrees. So it's either going to be like this. If it's an even degree polynomial, it's going to either be like this or like this. Which one is it? Yeah, down, because the leading coefficient is negative, right? So if you plug in like a million, this is going to be like roughly a million times a million squared times a million cubed, but negative. So yeah, this is the MBHS for sure. All right, good. So that's like point 1. Point 2 to notice is what is the like local behavior? If you just have to take a guess, because like, come on, man, duh. Like, what would you say is going on like near 2? I want to talk about what happens if you sort of like zoom. Okay, good answer. Yeah, I said, well, okay, so yeah, let me ask this question properly. What does this function, when x is approximately, which one should I do first? Let's do -2 first. When x is approximately -2, and this is actually deep, this is like basically calculus we're doing right now. If x is approximately -2, what value does this function have, approximately?
Or 0.
Of course, the common sense answer is it's approximately 0, right? Back when I used to teach Precalc, I had them all prove this theorem called the killer theorem. The killer theorem is that 0 times anything is 0. You can actually prove that. Corollary of the killer theorem, something really, really close to 0 multiplied by any number is really, really close to 0. And so yeah, if you give me a number which is really, really close to 2, then this factor is going to be approximately 0, and thus it will make the entire polynomial approximately 0, yeah? Okay, but I crave more information, because I don't actually want to know the value of this function at -2. I want to know the value of this function near -2. This is a calculus type question. Okay, so we do the following. We say, okay, when x is approximately -2, I would like to know what this function is approximately. And the answer is, well, this -2 is going to make this 0, right? And actually, if I'm a little bit less than, -2, then this is going to be negative. If I'm a little bit more than -2, this is going to be positive. So this is the factor which is changing sort of like radically as x changes a little bit. But these other numbers are not very sensitive to small changes in -2. For example, as long as x stays pretty close to -2, what is x minus 2 squared, basically? Basically just 16, right? Because if x is approximately -2, then -2 minus 2 is approximately -4, so this is approximately 16. You guys with me? This is kind of like a weird thick conversation. And how about over here? What is this approximately? No, careful, because it's -2, right?
-1.
-2 and 1, so that's -1 cubed is -1. And then there's also a negative over here that cancels. So I'm now going to make the bold claim that f of x is approximately 16 times x plus 2. Does everyone see where I got the 16 from? I sort of like held the x plus 2 constant, and I sort of evaluated the function at the rest. Alright, this says actually something quite deep about the behavior of this function. It says that if you zoom in and zoom in and zoom in and zoom in at this function near -2, what's it going to look like? Like a line, and not just any line. What kind of line? A line with a slope of 16, and that's actually like true. Alright, more. How about when x is approximately 2? What is this function approximately? Well, again, this factor will sort of change quite a lot based on small changes in 2. But this guy basically is just going to be, this is just going to basically be 4, right? And this one is going to be basically 27, because 3 cubed is 27. 27 times 4, wait, 27 times 4 is 108. And then there's also a negative. So I claim that when x is approximately 2, this function is approximately, I think negative 108, I think, right? Negative 108 x minus 2 squared. And again, I got that by keeping x minus 2 alone and sort of evaluating the function near 2. So what does that tell me about this function? If I zoom in and zoom in and zoom in and zoom in, at x equals 2, what is this function going to look like?
Quadratic.
It's going to look like a quadratic. Specifically, it's going to look like a quadratic, which has been moved over 2, well, you know, and which is upside down, and which is stretched out by a factor of 108. So what we can expect is this function to be locally negative quadratic near x equals 2. This is kind of the proof of this thing that you maybe like sort of just knew already. Okay, and how about the last one? When x is approximately -1, what can I say about this function? I think it's 9? 9?
Yes.
Because if I plug in negative
Yeah,
1
yeah,
here.
yeah.
No, I was wrong. Sorry. -1 minus 2. Oh, yeah. So that's 9, and then that's 1, but then a -1. So it's -9, right? So this is going to be approximately -9 x plus 1 cubed. And therefore, if I zoom in and zoom in and zoom in at -1, what should I expect this function to this polynomial to look like there? It should look like locally like x cubed, but flipped upside down and stretched out by a factor of 9. And so it's going to look like this. Yeah? All right. So this justifies this is locally linear, locally quadratic, and locally cubic. And then we also, of course, knew the end behavior as well, so we can therefore make a pretty good sketch of this function. It looks like, and then, cha, cha, cha. Agreed? Yeah. All right, good. All right, that was the lesson on sort of graphing polynomials. All right, a couple other things to note. Let's look at some other polynomials and see if they satisfy the fundamental theorem of algebra. How about f of x equals like 4? What's up with that? What is the degree of the polynomial f of x equals 4? 0. Yeah. So this is a 0 degree. We're all looking frame and stuff, right?
Barely. Yeah, you can, but there's like people in the way.
What's wrong?
There's like people in the way.
Oh, yeah. Then you gotta like make them like.
Dude, I don't know about that.
Yeah. Evan's helping by falling asleep, staying out of frame. All right. So this is a 0 degree polynomial. Fundamental theorem of algebra says how many roots does a 0 degree polynomial have?
0.
0. Is that true?
Yeah.
Yeah, it's true. Okay, but now you should start to panic a little bit. And someone brought this up a while. Nate brought this up a while ago.
F of x equals 0.
Yeah. What about f of x equals 0?
Isn't it like 0?
How many roots does f of x equals 0 have?
A lot. Infinite.
It's like every number is a root. Okay, so I don't want to necessarily say too much about this right now, but I'll just note that in many contexts, this is like not a 0 degree polynomial. For reasons like this one, because we really love the fundamental theorem of algebra and want it to be true always, the 0 function is actually like something different than just any old constant function. It's kind of like its own category. And I think technically some people will define it as a polynomial of degree like infinity or negative infinity, I can't remember which one, or like -1 or something weird like that to make it all work. I think I want it to be of degree, can't remember. Yeah.
So can't you just take like 0x to plus 0x squared plus 0x cubed all the way to infinity, and that's an infinity degree polynomial, but it's still f of x equals 0?
Yeah, something like that. Yeah. Yeah, because you want certain rules to hold. Like for example, if you add a 3rd degree polynomial to a 5th degree polynomial, what do you get? A 5th degree polynomial, yeah. So like the arithmetic for adding degrees of polynomials is you just like take the bigger one, right? Okay, but then if you multiply a 3rd degree polynomial by a 5th degree polynomial, what do you get? 8th degree polynomial. So you want the rules of, right? Yeah. So you want the rules of adding polynomials of certain degrees to be like you multiplying, you want it to be that you add the degrees. So then based on that, I think people assign a certain degree to 0, but I can't think of it right now. Let's move on. All right, a couple more examples really quick. Take the function f of x equals x squared plus 2x plus 5. Does this satisfy the fundamental theorem of algebra?
Yeah. With complex roots.
Yeah, this is exactly why we made this kind of qualification, right? This has no real roots, but it does have complex roots. And what are they? You know, we can always just do it, right? It's -2 plus or minus the square root of b squared minus 4ac all over 2. So what is this? That's like
Minus 1 plus
so it's like -2 plus or minus, that's like negative root 16, so that's like 4i over 2. So I guess this is -1 plus or minus 2i. Okay, so this is kind of one of the main reasons why we study complex numbers in high school, because like you sort of need them in order to make any kind of generalizations about polynomials, even if all you care about is polynomials with real coefficients, which is basically what we care about. We still have to let complex numbers into our heart, so we can say things like the fundamental theorem of algebra. All right, good. I got one more challenge for you. Take the function f of x equals x to the 4th plus 1. What is the degree of this polynomial? 4. So fundamental theorem of algebra says 4 roots. Find them. Go. Go. You gotta do some work. You're not just gonna be able to think about it. Well, go for it. Try. Try it. Do whatever you need to do, man.
Minus I. Why isn't I regular? So when you first start, you get x squared minus I. Oh no, it's times minus I. Wait, no.
No, the root is just x squared. You have to get
No, because like 4th degree polynomials is like
Because x squared.
Yeah, then you move it up one. Yes, Carl.
and then it's really tall.
Okay, you might be tempted to say like root I, but that's crap. That's not really an answer because I don't even know what that is. If it's truly a complex number, I want it in complex number standard form. A complex number is a number of the form a plus bi, where a and b are real. I will only accept answers in that form. Go. This is within your power. You know how to do this. It's something you learned last year. This is the thing that you learned last year.
Yes, sure.
Can you do it to some? But I too.
Yeah, I just worked as an expert.